Welcome back. We're at the end. We're approaching the end. I don't know about you, but I'm ready to be ended. So I've got the schedule up for the rest of the semester, so I'm not going to update it anymore. It's just the next couple weeks. We have one more assignment that's going to fully count. So this is the one that was due, posted a couple weeks ago, the web work assignment that was technically on the last test on Friday, right? It was substitution. And I just said, oh, well, you don't have to do all of it. It'll be due the next week. And so that's this one. And then I've also posted what I will consider 3 optional bonus web works for next week. And they're optional and bonus in that they're worth 0 points. If you go on there, all the questions you can see are worth 0 points each. And every one you answer, I'll take those points and add it into some previous homework assignment. Just to kind of reduce the end. I'm at the end of my rope, and I think a lot of you guys are too, just in terms of just being online and trying to wrap up and cram it all in. So that's my way of trying to ease that a little bit, but also give you a little bit of an extra credit opportunity, especially if you didn't have some great homework assignments. You can make up for that a little bit. There's 9 points out there. I think maybe 14 points. And it's related to stuff that we're going to talk about right now and over the next week. I don't think some of it's a little tricky, but some of it's taking what we're learning and just thinking about how it applies. And so if you kind of understand what we're doing, I think these bonus points shouldn't be too bad, is kind of what I'm thinking. Okay, I'm still working on test 3, and there's still a couple people out there that need to take that. 1 or 2 who are in this session. So I'd love for those people, if you're listening right now, to get in touch with me today. Like send me an email right now or send me a private message or something so we can figure out when you're going to do that. And then I don't think I've announced this before, and I actually just kind of figured it out last week, but I'd like to do the final next Friday, if that's possible. In class, it'll be our last Friday session. Otherwise, it would have to be like the following week, not on a Friday, and we're not used to coming into school not on a Friday. So that's why I was sort of thinking that would work. And the way I'm going to do the final, it's just going to be a combination of topics from test 1, 2, and 3. And so the stuff we're doing right now, in other words, will not be on the final. That's why it's optional homework. But very much applicable, by the way. The stuff we're learning now, especially if you're going to take Calc 2 or you want to use math in your own subject, like the stuff we're going to do today, tomorrow, next Monday, is really useful. If you can't make next Friday for one reason or another, I'd ask that you get in touch with me, and I just see John's message. If you can't make it next Friday for some reason, let me know. So, it's no different. We should be in class next Friday. So technically everyone should be available next Friday, but if you're not for some reason, let's figure that out. Sort of lost my train of thought. I was just talking about the topics. The topics are nothing that we haven't seen already. It's just going to be all the things together. So you can bring in all your note cards. I would suggest, or I suggested that you save those over the course of the semester and bring those in, use them on the final. And so here's what we're up to. We're going to do integration by parts today and Wednesday. And we have I noticed we have to finish a little bit from substitution. We do not have class on Friday. It's one of the wellness days. And then we'll learn about some interesting applications of integration on Monday, kind of what I would consider like a wrap-up class. Like, oh, we've done these cool things with integration. Here's a few things you can do with it. And we can do as much review as you want on Wednesday. It's totally up to you. And then again, I'd like to do the final in person next Friday. So Rashid just asked, can we bring 1 note card? Can anyone answer that question? Because I literally just said...
Yeah, I hear you, but I want to make sure I hear very well.
So what did you hear?
So I hear that you can bring your note cards.
Yeah. Sounds like you can bring a note card then. That's absolutely correct.
So I was trying to make sure if we can bring 1 or all of them. Like
you can bring. I'm suggesting that you can bring 3, like 1 from each test. That way you don't have to like make new note cards. If you just kind of held on to them, you could just bring them all in.
Okay, thank you.
Tyson's asking the class time with the final be 11 to 12:15 or both sessions 12 to 1:45. So I'm hoping just to keep the normal schedule. So if you usually come at 11, you would come at 11. If you normally come in at 12:30, you'd come in at 12:30. If you're interested in doing it earlier for some reason, that would be fine too. Or if you wanted to do one or the other session, I'd rather people just stay at their session because we have to think about social distancing and splitting up classrooms and all that stuff. But if there's issues, again, like some people bring up, I suggest you get in touch with me soon. If you like wait till next week and then you say, oh yeah, I can't do this, that's not okay. Will there be new material on the final? Does anyone also just covered that? And this also says it right here on the screen. Does anyone remember what I said about whether or not there'll be new material? There's not being new material. It'll be the same material from tests 1, 2, and 3. That's why the homework that's due next week is optional. Anything else I can repeat? I'm just kidding, guys. I'm happy to say that as many times as you want. Other questions? I really don't mean to deter questions. If you missed something, I will say it again. Anything else? All right, cool. I think that's all I really wanted to say. So I'm going to open up the notes and, oops, didn't mean to open up that, but that's okay. I happened to just notice when I was looking through the notes this morning that we didn't finish the substitution notes. Am I correct about that? Correct me if I'm wrong. And when we were preparing for the test, we did a bunch of examples. I think we did like a bunch of homework examples and some of the ones from the review I posted. But I forgot that we just didn't finish this. I'm right about that, right? I mean, obviously it's not filled in. I must not have realized that. So I apologize, but we did do a bunch of these examples, and I hope that that prepared you for the test. I haven't looked at that problem yet, though, so we'll see how that goes when I get there. Anyway, let's. This is a good way to finish up. Maybe review substitution in case you struggled with the particular topic on that last test. And so in these two problems on the last page of the substitution notes, we've got bounds on the integrals, right? So these are what we call definite integrals. And so we're going to get, some number out of this when we do the integration. And we talked about two different methods of doing it. You can see they're right above here. You either change the bounds and don't plug u back in, or you plug u back in and use the original bounds. And we did it both ways in both the examples up top here. I think to kind of finish off, maybe I'll just do one way and the other way, just to give you options again. And again, I apologize. I haven't actually looked at this test or this problem on the test yet, so I don't know if this is clear to you or not. But good review anyway for the final, which we'll have to do this next week. So on this problem, we want to look for something, right? We want to let u be something, and whatever u is, it should be something else in the problem. I'm sorry, when you take the derivative, it's something else in the problem. So what is u in this case? We had one like this on the test, actually kind of similar.
X squared.
Yeah, nice, x squared. I think Janetta's realizing that because when you take the derivative of x squared, so that's going to be our u, we get 2x dx. And that's really nice because we have a 2x and a dx like right in the problem. And so we don't need to do anything funky with the constant or anything like that. We just literally replace the x squared with u, and then the 2x dx is going to become du. Right, so that makes the substitution really nice and easy on this particular problem. Gosh, my pen is having some serious issues this morning. And so the original integral, I'm just going to rewrite it like this. The original integral, we see that this piece is just the u right here, and this piece is going to be the du. And it just becomes a very, very easy, or as easy as they can get, kind of integral, right? We just go from pi over 2 to pi of cosine u. Right, so we started with this like product of a trig function with the polynomial, do a little substitution, and it turns out we can just think of it as just the integral of cosine, which is one of those easy integrals, right? We don't have to worry too much about this. We just know that that turns into, now I have to remember, derivative of sine is cosine, so cosine becomes sine, right? Positive sine. And so this just turns right into, oops, we want to do the integration, sine of u, and then we just plug the points in. Well, before we plug the points in, we need to decide what we're going to do on that. But this is the kind of thing that, on the test, if you kind of went this far, you get lots of the points. Questions about the substitution part? Anyone still a little bit shaky on that, or? And so then remember what I just mentioned a second ago is you have two options. You can either replace the bounds and don't plug u back in, or plug in u and use the original bounds. Seen a couple examples of both those things, just in the interest of space and time here. We'll just do one on this one and one on the next one. So let me copy these instructions so I can paste them onto the next one. And then on this particular one, I don't know, let's just do, what's the second one look like? Do I want to plug pi into the bounds? Let's just not plug them in. So I'm going to use I'm not going to do this one. Let's plug in and use the original bounds on this one. Just looks like it might be easier. Okay, so instead of just using sine from pi over 2 to pi, that's where we ended, we plug u back in. Let me just pause for one moment there. Looks like I was just catching up with my internet. So I don't know what you guys did or didn't hear, but what I'm saying is, notice here I plugged u back in. So from here to here, u is x squared. And then I'm keeping the bounds, right? So it's still pi over 2 to pi. We don't have to mess around with that. We just plug the bounds in. And at this point, it just becomes a simple problem. It becomes sine of pi squared minus sine of pi over 2 squared. And pi squared is not a typical number on the unit circle. So if you're thinking like, oh, how do I do this with my head? We would use a calculator for this particular problem. I used a calculator ahead of time and I got approximately 1.05. Like pi squared is not one of those typical spots on the unit circle. Okay, what do you think about that? Feeling kind of good about substitution? I know some of you guys are kind of what I would call turning the corner, where it's not that bad anymore. Kind of understand what's going on. Jeanette is just unmuting to answer questions like crazy. She's just all over it. So this will be on the final, though, just to be clear, right? This is the last kind of thing that will be on the final. Questions about that? Okay, so this next one's kind of, I don't want to call it easy, but maybe once you see what u is, it kind of is easy. It's easy. It's so easy, it's tricky almost. That's how I kind of think about this one. Right, so, and the tricky part is thinking about what u is, because we want u to be something where we take the derivative and it's something else in the problem. But that's not exactly the case here. So thoughts about what we might want u to be? Maybe just everyone think about that for 1 second. If anyone wants to type it in the chat, or welcome to unmute and say it as well. Curious what you're thinking. What would u be in kind of a not too bad of a function? Ideas?
Would it not be 12 minus 5y?
It would be 12 minus 5y. And I think why were you thinking that, Janetta? Can you clarify why that came into your mind?
Well, when you make it du, you can, what's it called, get out 12, and then it would be 5y, and then just divide it by 5, negative 5.
Yeah. Right. So I think what Janetta's pointing out is when you take the derivative of 12 minus 5y, you just get a constant. And we know how to handle constants when we have this situation, right? When we have something that looks like du equals 5y, minus 5 dy, we look at the problem and we're thinking, is there a u in here? I mean, a minus 5, we're looking back, no minus 5. But we know how to deal with that, right? We just bring the minus 5 over to the other side, we divide it, and then it comes with us in the substitution. And so as long as, what Janetta is pointing out, and the reason that she sort of reached that point, so we do this, right, is we know how to handle constants when we do the substitution. And so we really just think about this as like a 1 over u squared, and we know how to integrate 1 over u squared. So let me just pause there and see if I can clarify something about that. You'll see the substitution in just a moment here. But something I can clarify so far? So let me do what I usually do, which is to rewrite the problem, right? So I'm going to just copy it over and then kind of think about what the pieces are. And so using the thing boxed in on the right there, we just said dy is going to become minus 1/5 du. And then the 1 over 12, the 12 minus 5y inside the squared is u, right? And so we're able to make a nice substitution with this, where it becomes du. And just to be clear, that's really, you can just pull the 1/5 out front, and then it's just u to the minus 2. And that's a quote unquote easy kind of one, right? Just the anti-power rule. So let me just pause there, see if the substitution looks okay. Question? All right. So we're going to do the second method, but let's, I guess, integrate this first. So the minus 1/5 comes along, we add 1 to the power, divide by the power, right? And now let's change the bounds. I'll still write 0, 2 right now, but on the next line, we're going to switch the bounds over. And can I paste in my thing here? Let's see if my genius plan worked. There it is. So we're not going to plug things in and use original bounds. We're going to replace the bounds this time. And so we just take u, and we take the bounds and we plug them into u, right? Let me just kind of review that by looking up over here. So the way you replace the original bounds, like it says up on this particular thing, is we change the bounds by plugging them into whatever u was, right? So like on this particular example, u was 1 plus x cubed. And so we took the old bounds, 5 and 1, we plug them into 1 plus x cubed, and we obtained new bounds. And that just is nicer sometimes because then you don't have to plug u back in. It's just the same. It's just like an alternate approach. And I usually just like to show both of them because you can choose whichever one you like. And like we just saw in the last one, maybe it's easier sometimes not to plug in pi and pi over 2 into something being squared, for example. Maybe we just want to not do that. So let's replace the bounds. So replace the bounds. We take the 2 and we plug it into u, which was what, 12 minus 5y. And we'll get 12 minus 10, which is 2. So that one actually stayed the same, oddly enough. And then 0 becomes 12 minus 0, which is 12. So instead of going from 0 to 2, we go from 12 to 2. And we keep it in the order too, right? So in other words, it becomes u to the minus 1 over 5. I'm just kind of carrying this down over here, right? U to the minus 1, I'm multiplying those things. The negatives cancel. And then instead of 0 to 2, we're going from 12 to 2, right? Because 2 stayed the same, but 0 turned into 12. And that's something that's easy to do. First, you plug in the 2, then you plug in the 12. And it looks like I didn't do this in the calculator ahead of time, but just to be clear, the negative ones make them into fractions, right? So this is really like 1 over 10 minus 12 times 5 is what, 60 over 10? I mean 1 over 60. That's not actually that hard to do. It would be 5 over 60. Is that right? Multiply that by 6, subtract 1. I think that's right.
Wouldn't it be 5 over 60 minus 1 over 60? Wouldn't that be 4 over 60?
It would be 6 over 60 minus 1 over 60, I think, right?
Okay.
And let's zoom in on that real quick if we have a question about that. This, you would do 6 over 6 to make it into 60, and then you get 6 minus 1.
Okay, yeah.
Thoughts? Questions? Concerns? Concerns most importantly. Okay. What were we doing? So this is a substitution. This is the end of the substitution rule, right? What were we doing there, by the way? We were undoing. So let me start over. Integration is undoing a derivative in some sense. That's one way to think about it. And so normal derivative rules like the anti-power rule does the power rule, so to speak, right? What were we undoing? What rule were we undoing when we were doing substitution? Do you remember? Anyone?
What's it called? When a variable is in another variable, what's it called again?
That's
Chain
called,
rule.
yeah, exactly. So a composition function or a chain rule, right? So this is the
Yeah.
thing when we were first learning about substitution, we were thinking about, well, what happens when we start with the chain rule? How do we undo the chain rule? Right? That's what the whole point of substitution was, just to kind of remind you of that. And I want to remind you of that because the next topic is undoing the product rule. Right? So that's integration by parts. Just read online somewhere where someone was trying to claim that this is the most important thing that they learned in the semester. I don't know if I would fully agree with that, but it's valuable. And if you're going to take Calc 2, usually this is one of the overlaps. So depending on what happens in a semester, who's teaching it, what the topic is, some people may or may not get to integration by parts. And so Calc 2 usually starts by reviewing integration by parts. So if you're going to take Calc 2, you'll start with a review of this, just kind of know that. Does anyone plan on doing that next semester? I think it's a good idea to kind of do it right away if you're planning on doing it personally. But anyway, let's talk about that. So I just, as a precursor here, this is the product rule, right? When you take the derivative of two things being multiplied, you do f prime g plus fg prime, right? We've seen the product rule a whole bunch of times throughout the differentiation section. And so now what we're thinking about is, okay, well, what if we integrate both sides of this? We want to undo the product rule. That leads to this, right? If you integrate that next row, it would look like what I just wrote down, right? So we now have an integral on both sides. And if we integrate the derivative, we just get the normal function back. And so on the left-hand side, this piece right here, you're just integrating a derivative. And so the derivative sign just goes away, right? And so we just get f of x times g of x. On the left-hand side, excuse me. And then on the right, we can break that integral up into the two separate integrals. Right? If you have two things being added inside an integral, you can just kind of think about them separately is what we're saying here. And so integration by parts, sort of, you can see, is starting with the product rule, but then we're going to rearrange it. We're kind of thinking about rearranging it into what's going to end up being this new kind of final method that we're going to learn. And so I'm going to take this piece right here on the middle piece there and subtract it over to the left side. And so that would be this, right? I don't know why I dropped my x's. Let me put the x's back in here just in case that's confusing. And if we just take this expression and switch the order in which it's written, we would obtain what's written down right below here. So from here to here, if we just switch the order, right? In other words, what I'm trying to say is this thing is just now written over here. You just kind of flip it around. And this is what we think of as integration by parts. So let me make that quick note. This is integration by parts. And this thing down at the bottom, the u dv v du thing, that's shorthand for the thing above it. And I think once we do a couple examples, this shorthand will make more sense. But notice how like it corresponds to the thing right above it, right? So we kind of think of u as being the f function, right? We think of dv as being g prime. So u, I think maybe the important thing to note is the middle one. We think of u as f and g as v. And so then du is the derivative of u, which would be f prime. So that's sort of the way to think about that. Anyway, we'll look at some examples and see how this works. But the takeaway that I'm trying to show you in this particular page is how we start with the product rule at the top. We're just rearranging what the product rule says. And then the idea is, if you're given something in this kind of form, if you're given something that looks like fg prime inside an integral, we can use this formula. And so let me just make that note. So if given an integral of the form integral of fg prime, we can use integration by parts. oftentimes people get really freaked out by integration by parts. I think it's partly a notation thing, right? That like is that thing I boxed in there is really ugly looking, and it's just a bunch of shorthand confusion, which is one of the reasons I like to try to cover it in Calc 1 as much as possible, so that if you do Calc 2, it's like a refresher or something that looks at least looks familiar instead of something that scares the crap out of you immediately in Calc 2. But I just know that it's the kind of thing that once you do a couple problems, similar to anything else in math, once you kind of see the way the notation sort of forms into an actual problem, makes you feel much better about it. And you can see the uses of it, right? It's one of the more useful integration techniques, which is why I think I read earlier today that's the most important thing someone learns in calculus or something. Anyway, so this is just the notation part so far. We're setting it up. The thing that we're going to use over and over and over again in this context, I'm just going to box it in again, maybe in a more careful way, is that thing that's now green. Right? The thing inside there tells us what integration by parts is. So before I sort of go into the actual process and do an example, are there questions about the notation or anything? There's not, I wouldn't expect anyone wants to hear anything too much, but this is a notation thing. Can I clarify anything about that?
It was just pretty much moving f prime g to the left. That's why it becomes negative, and then you set it equal to the right part of the product.
Yes, yeah, that's exactly right. So we started with this product rule up top here, this thing, and then threw an integral sign on it, and like you said, rearranged it. So subtracted a piece over to one side, and maybe that's kind of a strange thing to think about. Like maybe you don't think about this as being something you can move around, but it's just some expression that can be subtracted. So yeah, we can have something like this, for example, and be positive, and then subtract it over to the other side and have it be negative over on the other side. Yep, that's exactly right. Other thoughts or clarifications and things like that? All right, let's talk about how to actually use it. This is the thing that you actually probably want to know, and the thing that will be important moving forward, right? How do we actually use integration by parts? Well, as I just mentioned, you're going to be given something that looks like this. So it's going to be some function multiplied by some derivative. You're not going to really be able to tell necessarily which is the function and which is the derivative. And so here's how we actually choose which is which, right? So, so we need to choose one of those things to be u, and we need to choose one of them to be dv. And you can see if we look at the kind of, let me zoom in on the box here, whatever we choose to be u, over on the other side, we're going to differentiate it, right? And whatever we choose to be dv, over on the right side, we're going to integrate it. And so that helps us choose which is which. And it says that right here, right? So it says, we're going to differentiate u. And so we want to make sure that whatever we choose for u, when you differentiate it, it makes it less nasty, or nicer is some way that I like to think about that. I know that's maybe not, that's not a math term, obviously. You do something to make it less nasty. But when you integrate, when you differentiate polynomials, for example, the powers go down, right? And so they get nicer. So if you have a polynomial, for example, u is a good choice for the polynomial. As far as dv, let me do another color for that. The thing we choose for dv is just going to be whatever's left, right? So u is the important choice. dv is going to be defaulted to whatever's left. Okay, and again, the thing we choose for u, it means when we take the derivative, we want it to be like get simpler. Right, so like e to the x, for example, doesn't change when we take the derivative. So that's usually not a good choice for u. Same thing with trig functions, right? They just become other trig functions. So that's not a good choice for u. Okay, and if that's still not clear enough, I actually stumbled upon this acronym long after I took calculus about how to figure out what u is, right? So if you just want like a method to figure it out, this acronym right here, ILATE, is a good thing to choose. A good sort of method to choose what u is. And so you just go through ILATE one at a time and think, do I have this? Do I have this? And whatever you say yes, that's what you let u be. So I stands for inverse. L stands for logarithms. A stands for algebraic. What we mean by algebraic is polynomials. T stands for trig functions. And E stands for exponentials. And so when we choose U, we just kind of say, do I have an inverse? Yes or no. If the answer is no, go on to the next one. You just keep saying no until you say yes, and that's U. I know there's a little bit of writing there, so let me just pause and let people catch up. Let's see if I can clarify something there before we look at an example. Well, I'll finish the method, and then we'll look at an example. Thoughts about that acronym or what I'm trying to say in terms of picking U? You'll see it play out in just a second here, but. Okay, so once we have U picked, dv just ends up being whatever's left, right? And so then we differentiate U to get du. We integrate dv, excuse me, to get v. And then we just plug them into the formula, right? uv equals the integral of v du. Right? We just rewrite this in the new form with all the different pieces that we've calculated along the way. And then you'll see that the right-hand side of this, right, we're going to end up with something that looks like this. And so U and V are just going to be two things multiplied, and there's no instructions there. But the second half, the integral of v du or duv, is something you actually need to do, right? And so that's the last step. The last step is to evaluate the last integral and simplify. And something to note is that sometimes you need to do integration by parts again on that piece. So I'll just sort of say, may require more work. Hate to say it, but sometimes you got to do integration by parts twice. Or maybe it's really fun. I don't know. Maybe you can pretend it's fun or something. Does that ever work? Yes, super fun. Tyson's into it. That can be fun. I mean, gosh, man, I wouldn't have studied math this long if I didn't get some enjoyment out of it, or at least think it's useful or something. So it can be. Throw that out there. Right? Isn't it kind of fun sometimes where it's like something's really hard and you just kind of get it? That's fun. I don't know, is that fun? Maybe it feels good. I don't know. Anyway, let's do an example. Can I answer a question before we look at an example? All right, so as I just mentioned, choosing U is the big important part here, right? So on this first example, let me write down this acronym, I-L-A-T-E. We want to let U be whichever thing we have in there first. And we're looking at this example, and I see an e to the x and an x. And so is there an inverse? No. Is there a logarithm? No. Is there an algebraic? Yeah, so algebra, as I mentioned before, usually means polynomial. And so that's the thing that we're going to choose for U. And so we're going to let U equal the algebraic thing in here, which is x. How's that look? Right, it's definitely not the exponential, because the exponential is the e, and that's way on the end. So we got to algebraic first. I guess I should also mention, I should have always started here. I take this for granted sometimes, I apologize. We don't have a rule to solve this problem, right? E to the x times x is not one of the rules we have, and its substitution isn't going to work either, right? If I let U equal x, du equals 1. That's not helpful. If I let U equal e to the x, du is e to the x. That's also not helpful. So substitution doesn't work. It's not one of the rules we have. We need a different method. Sorry, I should have started there. That's why we're using integration by parts. And is it also clear that U should be x? It's okay. Okay, so we pick U, and as I mentioned up here, dv is just whatever is left. And so if U is x, that automatically implies that dv is e to the x. Okay? And now we're on the bullet point that's right at the top of the page here. We're going to differentiate u and integrate dv. And so from here to here, we'll differentiate. And so du equals 1. And then we integrate dv. Right, remember d means derivative. So if we want v, we want to integrate. And in this case, it just stays the same. And now we have all the components of the thing I'm about to circle here in green, right? We have all the things inside that box. We have u, we have dv, we have v, we have du. And we can plug it in and you'll see we get something that we can actually work with. So let me switch colors here. So what we found was the integral of u dv equals uv minus the integral of v du. I'm just copying down what was on that last page so I can scroll down. And we have all those things labeled right on the page right there, right? And so this becomes integral of x e to the x, that's what we started with, equals uv, so x e to the x, minus the integral of v e to the x du, which is 1. And that's easy, right? X e to the x on the right, this thing right here on the right side, we're just done with that. We don't have to do anything there. There's no instructions. It's just x e to the x. The second piece, we need to integrate this. But we can do that because it's just e to the x now. And that's an easy thing to do. And so that's how we would finish this one off. Right? We would do this integral. Evaluate that. That's a dx situation, by the way. And so that's pretty easy, right? That just becomes x e to the x minus e to the x. And what do we throw on the end after we finish off an indefinite integral?
Plus c.
Plus c.
Plus c. Thoughts? What do you think? And notice this. You can always double check these things, right? If you differentiate this, you can get back to the original. So if we did d over dx of this thing, we end up with a product rule in there. The first thing's a product rule, but it's like an easy product rule. The c goes away, right? Notice what happens here. We'd get f prime g plus f g prime. That stays the same. The c goes away. And look at this. These two things cancel. And we get right back to the original. So you can always double check those things, right? What do you think?
So that part that we evaluated before to get the answer, are you taking, is that taking the antiderivatives of each number?
The thing that I'm circling right now, this?
Yeah.
Yeah, you're doing the antiderivative there, right? It's an indefinite integral because it's got the integral sign dx. And so, but what's the antiderivative of e to the x?
E to the x.
Yeah, it just stays the same. So that's why it kind of looks like we didn't do anything, because it just stayed the same.
But then wouldn't you have to take
That's what
the
the antiderivative is. Sorry, go ahead.
I was just gonna say, then wouldn't you have to take the antiderivative of 1?
No. So, anything's multiplied by 1. The 1 part just came from the du. I was just trying to be clear that, right, this du ended up being 1. And so e to the x times 1 is just e to the x. Right, so I just wrote the 1 there just to be clear that we didn't forget about du. Du was just the number 1.
Okay.
Yeah, thanks for that clarification. Other things like that? All right, let's do one more. And I don't know. I was gonna say you could probably do this one, but maybe we should just do it together a little bit. But help me walk through it, right? So let's do ILATE again. Do I have any inverses, logs, algebraic, etc.? Most of the, not most of the time, but a lot of times it ends up being algebraic, honestly. So there's no inverses, right? There's no logs. We do have algebraic again. And that's just a polynomial. And so we're going to let u be the 2t. And that means that du is just whatever's left. I mean, dv, excuse me. And I think that the notation is critically important here. If you understand the notation, then the next step is obvious. If you have u and you want du, you
Then you find
differentiate.
then it'd be 2.
Right, 2. Excellent. And if you have dv and you want v, you integrate. Right, and so what's that? So du, like I think that was Janetta just said.
So
2.
then so v would be cosine.
Cosine.
Negative cosine.
Yeah, minus
Negative,
cosine.
my
I always have
fault.
to double check that myself. Minus cosine. But then, this is the hard part, so to speak, because then once you have all these different components, it's literally just a matter of putting it into that formula. And then the integral that you need to do should be an easy one, because you should have sort of gotten rid of the hard part. Unless you need to do it a second time, which we'll see. We won't see that today. We'll see that next time. And we just sort of stop here and see if this looks okay before we write down the answer. All right, let me copy the method again. So it was the integral of u dv equals uv minus the integral v du. Right, I'm just copying down what it says right at the top of the page there. And we have all these components. And so I just like to write that down so you can see how they all fit in. All right, so our u in this case was 2t. Our dv was sine. And then when we integrated and differentiated, we ended up with the following, right? So u is still 2t, but now v is minus cosine. And then v du would be minus cosine times 2. And that integral on the right is not too bad, right? Let's simplify it a little bit so it doesn't look so bad, but that's a minus 2t cosine t. And then the 2 minuses there cancel into a plus, and we'll have plus 2 integral cosine. That's pretty easy, right? See if that looks okay. So we get a plus in the middle because you have a double negative that cancel there. And cosine just becomes sine. So we're right at the end here, right? We just do the integration. And that's it.
So at the end, we do integration.
So you're just following the instructions, right? So this tells you right here to integrate. Right, when you've got something sandwiched between the integrand, which is the S thing, dt, that means do the integral. Yep. And also that's where the plus c comes from, right? Because it's an indefinite integral, and so you get the plus c from that piece.
Okay.
And you can double check this, right? If you take the derivative of this, you should get back to the original. So that's good practice, like for the final, for example. I could definitely ask you to take the derivative of this final piece on the final, just for example, right? You get a product rule. This would end up being a product rule if you did that, and then stuff will cancel and you'll get back to the original. Ooh, ow.
Hey, Professor, what's an inverse?
Yeah, so that's a good question. Thoughts about inverse? What do people think an inverse is?
Yeah.
So it means like something to the -1. So like that would be an inverse thing. Just like 1 over.
And if you see that, that takes priority. That becomes you.
That takes priority. Yeah.
Okay.
Yeah, I'm just doing a quick search here just to make sure I'm not missing some other particular type of inverse. Talk specifically about inverse trig functions potentially. So I'd say that one doesn't come up a lot. Let's add a note to that up by the ILate part, the original part. And so what I'm seeing just on these couple examples, I'll just Google quick, usually is that the inverse means trig inverses. So things like cosine to the -1 or sine to the -1, tan to the -1, etc. We don't see though, we don't do a lot of trig in Calc 1, at least not in this version of Calc 1. I've mentioned this a couple times. Trig, in my opinion, comes up more so in Calc 2, but in these kinds of contexts, right? I mentioned that integration by parts is really a Calc 2 concept. And so you start to really build in some of the trig stuff in Calc 2. Yeah, so inverses, I believe, are trig inverses specifically. Other thoughts? Okay, I'm gonna let this be our little shorter period today. We'll finish up these notes on integration by parts on Wednesday, and it's really just, you know, obviously the next step is doing a definite integral, right? So putting bounds on it, and it's just putting bounds on the thing we just came up with. So it's no different what we just did. We'll just have an opportunity to try it again and move forward with this. Do a couple examples. We'll do one where we have to do it twice. So we'll just kind of explore this a little bit more on Wednesday. That's all I've got, folks. Thank you very much. I'm stick around if you need anything. I've got office hours this afternoon as well. And I'll be working hard to get those tests graded over the next day or two. About a third of the way through, I'd say. Thanks, everyone. Have a great one.
I'm sorry, I know you said it, but when should we expect our grades for 3?
As soon as humanly possible. I did see an email come in that someone wanted to take it on Wednesday. So my goal would probably be, if everyone's done taking it on Wednesday, I would try to return it maybe Wednesday night or something.
All right, no worries.
Hey, Professor, what is linear algebra? Does that have to do anything with calc? Because I'm now the fall semester, I'm scheduled to take Calc 2 at the same time as linear algebra. Is that recommended, or how do you feel about that?
I think that's okay. Yeah, that's okay to do. I think I'm teaching linear. Is that right?
I don't know.
No, I'm not teaching it. Yeah, linear is a great class. Calc 1's a prereq, but it really doesn't have anything to do with Calc 1. It has nothing to do
Okay.
with calculus. That prereq is like a math maturity prereq. It's like you
I
should
got
only
you.
take this course if you can handle the type of math that you do in calculus, but you don't use calculus in linear algebra at all. So
Okay.
it's a study of matrices and things like that, which I personally
Vectors and
found
all
to
that.
be really interesting as an undergrad. It was like something that wasn't calculus. You know, you do like pre-calculus, you do calc 1, you do calculus. It feels like math is just calculus, and then you do something different in linear algebra, and it's like, oh, you can do cool stuff with matrices and things. So anyway, yeah, I wouldn't think there'd be a problem for you to do both those at the same time.
All right, because I thought like the concepts like overlapped. I need to know Calc 2 before I take linear, but okay, I guess not.
Nope, no, they don't.
All right, cool.
Professor, I just have one more question on that last point.
Yep. One more
You
question.
only integrate the last part of it.
Yes, you only integrate the last part. Yep. So notice how this is trying to say, like, you start with something that looks like this, transform it into something that looks like this, but the second part's the only thing that has an integral on it.
Okay, just checking. Thank you.
What's everyone else up to? Got a lot of people hanging out. Matthew, you there? Matthew Harrington, hello.
That's awkward.
Mr. Harrington. What if I send him a message? A private message. No one will get it except him.
Thank you. Have a good day.
See ya.
So I sent you an email about the final confrontation.
Yeah, I saw that. Let me just stop recording here. There's no reason that this needs to be on recording.